Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss the branch current method and the loop current method. The objectives for this video are just that you will be able to apply each of these methods, the branch current method and the loop current method, to find an unknown quantity in a circuit. Before we begin, we have to provide a few definitions. First, a loop is a complete current path within a circuit. Notice on the example, there are two loops. Loop 1 is on the left, loop 2 is on the right. It's simply a complete closed path within a circuit. A node is a point where two or more components are connected. Notice on this picture, we have four nodes: node A, node B, node C, and node D. A branch is a path that connects two nodes. So on this particular circuit, this is a branch, this is a branch, this is a branch, and this is a branch. It's a path that connects two nodes. We're going to use these three definitions as we discuss these different methods for circuit analysis. The branch current method is a method you can use to find an unknown quantity in a circuit. You begin by assigning a current to each branch in the circuit. You can decide what direction you want that current to be. It's completely arbitrary. Your answer at the end of the problem will tell you if the direction you picked was correct. If not, you would simply reverse the direction of your current when continuing to study the circuit. So you're going to assign a current to each branch. You're going to show the polarities of each resistor voltage based on the current you picked. You're going to apply KVL around each closed loop and KCL at least one node, maybe more, so that all branch currents are included. This is going to give you a series of equations, and you're going to then use algebra or a matrix to solve these equations in order to get your unknown values. This method will allow you to find each branch current in a circuit. So here's an example. In this example, we have two sources, a 10-volt source and a 5-volt source. Keep in mind that we've already discussed superposition, and that's another theorem you could use to analyze this circuit. Today's focus, however, is to learn a different tool, which is the branch current method. With this method, we'll be able to find the branch currents, which are labeled here, I1, I2, and I3. So to begin this type of problem, the first thing you would do is assign each branch current. And this example, that's already been done for you. If your picture had no arrows and no polarities, you would manually draw them yourself. So the branch currents have been assigned for you. The polarity has been assigned for you, again, because this is an example. However, going forward, you'll be given a blank circuit without any directions or polarities, and you will have to assign them yourself. Step 3 is to apply KVL around each closed loop. Here's my first equation. I'm going to start with the left loop. I'm going to start right here and go around clockwise. That would mean the voltage for R1 plus the voltage for R2 minus 10 volts has to equal 0. Or we can rearrange that and say VR1 plus VR2 equals 10 volts. So I'm now going to replace each voltage in this equation with its equivalent based on Ohm's law. Ohm's law says that voltage is current times resistance, so I'm going to replace VR1 with 470 times I1, because the voltage for R1 would be the current going through this resistor times its resistance. And you're going to do that for each variable in your equation. So VR2 has been replaced with the resistance for R2 multiplied by the current going through R2, which has to be I2. This is our first equation. Next, we're going to apply a KVL around the second loop, around this loop right here. I'm going to start right here and go counterclockwise. So I'm going to get the voltage for R3 plus the voltage for R2 minus the voltage for the source equals 0. Rearranging that, I get VR3 plus VR2 equals 5 volts. Here I'm going to do the same thing as before. I'm going to replace VR3 and VR2 with its Ohm's law equivalent. So VR3 is 820 times I3. VR2 is 220 times I2. This is my second equation. Keep in mind, I'm trying to find three things. Each branch current, I1, I2, and I3. If I'm trying to find three things, I need three equations that gives me a relationship between those things. So far, I only have two equations, so I need a third equation. My third equation will come from KCL. I have one node, node A. I'm going to apply KCL to that node. According to KCL, the current going in has to equal the current coming out, which means that I1 plus I3 has to equal I2. So to recap, this is our first equation, this is our second equation, this is our third equation. From here, it's up to you to use algebra or a matrix to figure out the values for I1, I2, and I3. So in this problem, we're going to use algebra. In the next lecture video covering the node voltage method, I will discuss how to use a matrix. I'm going to use algebra for this problem. However, there's no reason why you can't use a matrix if you want to. Both of those solutions will work. You can review the textbook for more information on how to use a matrix. But for today, I'm going to use algebra to solve this. Here's one of my equations. I'm going to take I2 and replace I2 with I1 plus I3 in my loop 2 equation. So right here, I've made a replacement. And then I'm going to distribute that 220 to both terms. And I'm going to simplify that equation. From here, you can pick a variable to solve for. Solve for I1 or solve for I3. I decided to solve for I1. So I have an equation now that tells me what I1 is in terms of I3. My goal is to find a second equation that will also tell me what I1 is in terms of I3. So I'm going to stop right here. I'm going to go back to loop 1 and make a similar replacement and see where that leads me. So this is the equation from KCL. I'm going to go back to loop 1, and I'm also going to plug that in for I2 right here. Distribute, simplify, solve for I1. Now I have two equations that will tell me the relationship between I1 and I3. I'm going to take those two equations and set them equal to each other. If this is equal to I1 and this is equal to I1, then they're both equal to each other. Now I've eliminated I1 from the picture completely, and I have one equation that I can use algebra to solve for I3. So once you do that algebra, you're going to combine like terms. You're going to move I3 over to one side and get the other constants on the other side. So move this over here, add this to this side, and then divide. You'll get that I3 is approximately 1.86 milliamps. Now that I know I3, I can go back to this equation right here. Plug in I3 right here and get I1. Now that I know I3 and I1, I can go back to this equation right here to find I2. And that completes the problem. You now know the current through each branch. If you needed to, you could continue on by finding the voltage drop for each resistor, because now you know the current through each resistor. And that's the basic idea behind the branch current method. Keep in mind the algebra will look different for every problem, and it won't always be as straightforward as this one, you'll have to use your algebraic skills to be able to determine how you go about solving for your 3 equations. So that may be a skill that you might want to practice or brush up on if it's been a minute since you've had a math class. We'll do another example. This example has the same orientation as the example before, so we're just going to repeat all of those steps again. Notice that you have 2 sources just like before, 3 resistors, and you're going to find the branch current, which is shown in the picture as I1, I2, and I3. Notice this time I3 is flowing in a different direction. So we're going to begin by assigning each branch current. In this case, it was already done. Next, you're going to assign a polarity to each resistor voltage drop. So that means you need a plus and a minus, a plus and a minus, a plus and a minus. Now we're going to apply KVL around each closed loop. For the first loop, I'm going to start right here, go around clockwise, VR1 plus VR2 minus 12 equals 0. Simplify that. And then replace each voltage with its Ohm's law equivalent. V equals I times R. So VR1 has to be 8.2 times I1. VR2 has to be 10 times I2. There's my first equation. Next, I'm going to go to the next loop. I'm going to start right here and go clockwise. So I get VR3 plus 5 volts minus VR2 equals 0. In the next example, we're again going to use the branch current method to find the currents I1, I2, and I3 below. You'll notice that this circuit looks very similar to the one we just did, with different voltage and resistor values. We're just going to repeat the process of applying the branch current method to this circuit as well, so that you can gain familiarity with the steps. Notice that in this diagram, I1 is still going to the right, I2 is going down, but now I3 is also going to the right. This is also slightly different than the example that we just did, and this will change our KVL equations. So to begin, our first step is to assign each branch current, and this has already been done. Our next step is to assign a polarity to each resistor voltage drop. So I'm going to do that here. According to the direction of the current that was chosen, this is the polarity for each resistor. Now that I know those polarities, I'm going to apply KVL around each closed loop. So with the first loop, I'm going to start right here and go clockwise around the loop, which is going to give me VR1 plus VR2 minus 12 volts equals 0. Then I'm going to replace VR1 and VR2 with their Ohm's law equivalent, which is I times R. So my equation for loop 1 becomes 8.2 times I1 plus 10 times I2 equals 12. Now I'm going to do the same thing for the second loop. I'm going to start right here and go clockwise around the loop. In this case, I'll have VR3 plus 6 volts minus VR2 equals 0. If I simplify that, I get VR3 minus VR2 equals negative 6. And then I'll replace VR3 and VR2 with their equivalents using Ohm's law. So this equation becomes 5.6 times I3 minus 10 times I2 equals negative 6. Remember that I am solving for 3 things, I1, I2, and I3, which means I need 3 equations. This is my first equation. This is my second equation. My third equation will come from applying KCL to node A. According to KCL, I1 is going into the node, I3 and I2 are coming out of the node, and there's my equation for KCL. And here's a summary of the three equations that we just derived. Again, from this point, you're either going to use algebra or a matrix to solve for I1, I2, and I3. I'm going to continue using algebra for this session. So, I know that I1 is equal to I3 plus I2. I'm going to substitute I1 into my first loop equation right there. Next, I'm going to distribute the 8.2 to both terms and simplify. Next, I'm going to solve for I3. And basically, that means I'm just going to isolate I3. So that comes out to be 12 minus the 18.2 I2 divided by 8.2. If we simplify this fraction further, here's my expression for I3. Next, take a look at the equation for the second loop. I can solve that equation Okay, I'm starting here. Next, take a look at the second loop equation. Keep in mind that this is the equation that I've already found for I3 on the previous slide. I'm going to plug this value for I3 into my second loop equation right here. After that, I'm just going to distribute and simplify. And now I have one equation with one thing that I don't know, so I can solve this for I2. And I2 comes out to be approximately 632 milliamps. Now that I've found I2, I can take that and plug that right back into this equation here to find I3. That'll come out to be 57 milliamps. And now that I have I2 and I3, I can go back and plug into my equation for KCL to find I1. So I found that I1 is 689 milliamps, I2 is 632 milliamps, and I3 is 57 milliamps. Now, as you're doing these problems, if one of your currents comes out to be negative, that just means the direction you initially picked was incorrect and current is actually flowing the opposite direction from which you picked. It doesn't mean you have to change any of your calculations. It doesn't mean that you have to go back and redo the problem and change the arrow. It just means you need to be aware of the fact that current flows in the opposite direction from which you originally identified it. You just have to keep that in mind if you're going to go forward with this problem and calculate other values like the voltages for each resistor. Next, we're going to move on to the loop current method, which is quite similar to the branch current method with one exception. Instead of assigning a current to each branch, we're going to assign a current to each loop. So if you look at the picture here, we have loop current A and loop current B. So we're going to assign those loops in a clockwise direction around each closed loop. Then we're going to indicate the voltage drop polarities for each resistor in the loop based on those directions. And then we're going to apply KVL around each closed loop just like we did with the branch current method. However, in this case, when more than one loop current passes through a component, you have to consider the fact that there is two currents, IA and IB. Both of those currents will affect your KVL equation for that resistor. Then we're going to solve those resulting equations for each loop current. So here's an example. We have a circuit here with two sources, one 10 volt, one 6 volt, and three resistors connected in between. We're going to find the loop currents first. We're going to use those loop currents to figure out what each branch current must be. So to begin, here's a recap of the directions or the steps for the loop current method. So we have to start by assigning a clockwise current around each closed loop. There are my two loops, loop A and loop B. We also have here the polarities for each resistor. Here's the positive side, positive, for this loop. Notice that loop B flows this way. So when we have loop B, this R2 has a positive here and a positive here. So when we do the loop current method, if you have a resistor where there are two loop currents flowing through the same resistor, you're going to assign a polarity for each loop current, and then you have to consider that polarity when you write your KVL equations. And I'll explain that in a minute when we get to that calculation. So now that we have our loop currents and our polarities, we're going to do a KVL around each closed loop. Here's the KVL around loop A. If I begin right here and go clockwise, I would have negative 10 volts plus VR1 plus VR2 equals 0. Now I'm going to replace VR1 and VR2 with their equivalent expressions based on Ohm's law. I'm sorry, my loop B is here. I'll do that first. So loop B, if I start right here and go around the loop this way, here's my equation for loop B. Now I'm going to take each of these equations and fill in VR1 and VR2 with their equivalent. For VR1, we would have 270 ohms times the current going through, which is loop A, or we call that IA. Everything has been abbreviated to be kiloohms because we have different units in the circuit. So everything is now going to be written in kiloohms from this point for consistency. So VR1 is going to be 0.270 times IA. The voltage for R2 has to take into account that there are two currents running through it. So ultimately, we have to take the difference between those two currents because one is flowing down through R2. Loop A flows down through R2. Loop B flows up through R2. So we need to take the algebraic sum of those two currents. Since they're in opposing directions, that means we have to take the difference between them. So the current for R2 is going to be IA minus IB. Keep in mind when you select your current for this resistor, you're going to write the current for the loop you're considering first. Since I'm looking at a KVL around loop A, the IA comes first. So we filled in the first equation. The second equation, we're going to do the same thing. The second equation for loop B has VR2 again. Since now our perspective is loop B, we're going to write the voltage for loop B in terms of the difference between IB and IA, because this is the loop we're considering. So when you have a resistor with two loop currents going through it, if they're in opposing directions, you have to subtract them. To determine which one you write first, pick the current for the loop you're currently analyzing. We're analyzing loop B, so IB goes first. And then we subtract the current for loop A because it's going in an opposite direction from loop B. Fill in the voltage for R3. Oh, that should say R3. And now we have our two equations. I apologize for that typo. That should say R3 right there. Now we have our two equations, and we have two things that we don't know. Loop A and loop B, the currents for those two loops. So we can solve this using algebra or a matrix. Here's how you might start solving it using algebra. We're going to take this equation right here and solve it for IA. Take the second equation, isolate IA. Then take that value and plug it back into the first equation. Now you've eliminated IA, you can simplify this and solve it for IB. Once you get IB, you can very easily plug it back in here to find IA. Now we have the loop currents. Remember, the second half of the question is to also find each branch current. I1 would be here, I2 would be here, I3 would be here. So we can see that the branch current for I1 would be the same as loop current A. The branch current for R3 would be the same as loop current B. And the current for R2 has to be the difference between these two currents. So I1 equals IA. I2 is going to be the difference between IA and IB. Since IA flows down and IB flows up, we're going to take the difference between the two. IA is bigger than IB, so IA will come first. Take the difference between the two, and your answer is that I2 is 7.43 milliamps going down. I3, again, will be loop current B. And this is how we apply the loop current method. In our final example, we have another circuit where we're going to apply the loop current method to find both the loop currents as well as the branch currents for R1, R2, and R3. Here are our two loops, loop A and loop B. Notice that I've also have the polarity for each resistor based on the direction for the current flow. So positive, positive, and positive. Loop B flows this way, so positive here, positive here, positive here. So I have my loop currents and I have my polarities. Now I'm going to do a KVL around each closed loop. I'm going to start with loop A. I'm going to start here and work my way clockwise around the loop. That'll give me VR3 plus VR4 plus VR1 equals 0. For loop B, I'm going to start right here, go clockwise around the loop, and I'll get that VR1 plus VR2 plus VR5 has to equal 25 volts. Next, I'm going to replace each voltage with its Ohm's law equivalence. So for VR3, that's going to be 27 times IA. For VR4, that's going to be 52 times IA. And for VR1, that's going to be 12 times IA minus IB. For loop B, I'm going to have VR1 again. This time I'm going to have 12 times IB minus IA. Remember, whatever loop you're analyzing determines which current you're going to write first. So I have 12 times IB minus IA plus 15 times IB plus 20 times IB. Since these are in series and since these are in series, you could even combine those first before you write your equations. If you want to, that's fine. Now I'm going to simplify. So loop A comes out to be 91 IA minus 12 IB equals 0. And loop B comes out to be 47 IB minus 12 IA equals 25 after you distribute and simplify. Now you basically just need to use algebra or a matrix to solve this set of equations. Again, I will cover how to solve this using a matrix in the next video for the node voltage method. So there's my equations. You can decide which equation you want to work with first, but pick one. Pick one equation and isolate a variable. So pick an equation and pick a variable. You can pick the second equation and solve for IB. You can pick the first equation and solve for IA. It doesn't matter where you start, but pick an equation, pick a variable, and solve for it. So in this case, I picked the second equation and I solved it for IB. So 25 plus the 12 IA divided by the 47, and then simplify that. Now I have an expression for IB, that I can go plug in right here. So I'm going to distribute the 12 and simplify. And now I have an equation that I can solve for IA. Once I have IA, I can go right back here or here and plug IA into this expression to find IB. And that completes the first part of the problem. So I have the loop currents, IA and IB. Next, we're going to find the branch currents for IR1, IR2, and IR3. The current through resistor 1 has to be the difference between my two loop currents. And I'm simply going to take the difference by starting with whichever one was bigger. The current for loop B goes this way, and it's 550 milliamps. The current for loop A goes this way, and it's only 72 milliamps. So take the difference, and you'll know the current through R1, and the current will flow in the same direction as loop B, which means it'll flow to the right. The current for R2 has to be the same as the loop current for loop B. And the current for R3 has to be the loop current IA. And that completes the problem. So this is another example of the loop current method and how we apply that method. Again, if the algebra is unfamiliar to you, that's something that you'll want to brush up on, and make sure that you're comfortable being able to set up those equations and then figure out how to attack those equations to solve for each unknown variable. We'll go over more of this in the node voltage method, and like I said, I'll also show you how to solve these types of equations using a matrix instead of using algebra. And that is the end of this video.